If you rewind the universe all the way back, you don't just reach empty space. You go beyond that to the very beginning of space and time itself, the Big Bang. Think of this moment as time zero, the exact starting point of our universe. At this moment, the entire cosmos, everything we know, all matter, energy, space, and time, was squeezed into something unimaginably tiny. Scientists call this the singularity. Imagine a point smaller than an atom, hotter than the core of the brightest stars, and denser than anything we can imagine. The laws of physics as we know them break down here. Space didn't exist yet, and time, as we understand it, had no meaning. This singularity is the cosmic seed from which everything emerged. Then, in an instant, expansion began. This expansion marks the birth of space and time, the very foundation that allowed matter to form and even the invisible forces of nature to start shaping reality. Scientists use a special unit of time called the Planck time to describe this fundamental limit. It's about 5.39 times 10 to the minus 44 seconds, representing the shortest timescale physics can currently describe. Before the Planck time, our existing physical laws, such as Einstein's general relativity and quantum mechanics, ceased to apply. After the Planck time, as the universe cooled and expanded, the four fundamental forces that were once unified began to separate. Gravity was the first to break away from this unified force. Gravity is a unique kind of force because it's actually the bending and warping of space and time itself. Imagine space as a stretchy fabric, and giant objects like stars, planets, and black holes create dents in it. That's gravity in action. The other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, are somewhat different. They are explained through quantum field theory, which treats particles as ripples or waves on invisible fields spread throughout space. Because gravity is tied to the very fabric of space and time, it was the first to separate from the other forces at the Planck scale. Think of it as the stage itself, separating from the actors who will later perform on it. Later, at around 10 to the minus 36 seconds after the Big Bang, the strong nuclear force separated from what physicists call the electroweak force, a combination of electromagnetism and the weak force. This event is known in physics as a symmetry breaking, a kind of cosmic phase transition where the perfect unity of the fundamental forces fractured, allowing distinct forces to emerge. This marked a critical change in the structure of the universe and possibly triggered cosmic inflation, the brief but dramatic period during which space itself expanded exponentially faster than the speed of light. This wasn't like a fireworks explosion sending bits flying out into empty space. Instead, space itself stretched and grew faster than the speed of light. But don't worry, this doesn't break physics. It's the space between objects that's stretching. But during inflation, the energy from this transition became locked in the inflaton field, the field responsible for driving inflation. As the universe expanded rapidly, its temperature dropped sharply, and any existing particles were stretched and diluted into near nothingness. The universe became cold and nearly empty, despite still holding an enormous amount of latent energy. It wasn't until inflation ended, around 10 to the power of negative 32 seconds, that this energy was released in a process called reheating. As inflation decayed, energy from the inflaton field re-excited suppressed quantum fields. While no real particles yet existed, their seeds were now in place, awaiting the moment mass could emerge. The next critical transition came around 10 to the minus 12 seconds after the Big Bang, when the universe cooled to about 100 giga-electron volts. At this threshold, a dramatic shift occurred. Electroweak symmetry broke. The electroweak force, once a single unified force, split into two. The electromagnetic force, responsible for light, magnetism, and electricity. The weak nuclear force, responsible for beta decay and neutrino interactions. This is when the Higgs field came into play. It interacted with particles across the universe, giving them mass through a process known as the Higgs mechanism. For the first time, quarks, electrons, and other fundamental particles became massive and physically real in the sense we understand them today. Now that quarks had mass and energy, they could begin to interact under the influence of the strong nuclear force. This set the stage for the formation of the Quark-Gluon plasma, QGP, a hot, dense state where quarks and gluons moved freely in a chaotic particle soup. These particles can be roughly divided into two categories. One category consists of fermions, the fundamental building blocks of matter. Among them, quarks are especially important. They are the basic units that would later combine to form protons and neutrons. The other category is made up of bosons, the carriers of the fundamental forces. In this particle soup, one of the most active bosons is the gluon, which transmits the strong force. It acts like an invisible glue that binds quarks together. In addition, another class of bosons, known as electroweak bosons, also existed at the time. The photon, as we know it today, eventually emerged from this group after the breaking of electroweak symmetry. About 10 to the power of -5 seconds after the Big Bang, the ambient temperature dropped below approximately 170 mega-electron volts. At this critical point, the strong nuclear force finally took full control, and the universe underwent a phase transition known as the QCD confinement transition. During this moment, free quarks and gluons, which had been moving independently in the Quark-Gluon plasma, were no longer able to exist freely. Instead, they became permanently bound together by the strong force into more stable combinations, called hadrons. Among these hadrons, two types were especially important: protons, made of 2 up quarks and 1 down quark, neutrons, made of 1 up quark and 2 down quarks. Now, for the first time, stable composite particles, the precursors to all matter in the universe, began to take shape. From this point onward, quarks would never be seen alone again. They were locked inside particles by the strong force, like marbles held together by an invisible rubber band that only grows stronger as you try to pull them apart. Roughly between 10 to the -6 seconds and 1 second after the Big Bang, matter and antimatter existed in nearly equal quantities. For every quark, there was an antiquark. For every electron, a positron. These particle-antiparticle pairs frequently collided and annihilated each other, producing high-energy photons, primarily in the form of gamma rays, and filling the universe with intense radiation. This annihilation process occurred as the universe cooled from temperatures around 10 trillion Kelvin, about 1 mega-electron-volt energy scale, down to lower values. However, the annihilation was not perfectly balanced. For reasons still not fully understood, possibly related to CP violation and baryogenesis, a tiny asymmetry existed. For approximately every 1 billion matter-antimatter pairs, there was one excess matter particle. When most of the matter and antimatter annihilated, these surviving particles, just 1 billionth of the original total, went on to form all the structures we observe today: galaxies, stars, planets, and life itself. Around 1 second after the Big Bang, as the universe cooled to about 1 billion Kelvin, neutron-proton conversions via the weak nuclear force came to a halt. This freeze-out locked in a neutron-to-proton ratio of roughly 1 to 6. That is, for every 6 protons, there was 1 neutron. Because free neutrons are unstable, with a half-life of about 10 minutes, they began to decay unless captured in atomic nuclei. This decay would shape the chemistry of the early universe, setting the stage for the next critical step, nuclear fusion. Big Bang nucleosynthesis, the era when the first atomic nuclei were forged. For the first few minutes, there was a problem known as the deuterium bottleneck. Only when the universe cooled further, after about 3 minutes, did deuterium become stable. Once that happened, things moved quickly. Deuterium nuclei began to fuse into helium-3, helium-4, and even trace amounts of lithium-7. This cosmic fusion factory ran for only about 20 minutes. After that, the universe had expanded and cooled too much for fusion to continue. By then, the results were locked in. About 75% of the mass of the universe was in the form of hydrogen nuclei, single protons. About 25% became helium-4, tiny traces of deuterium, helium-3, and lithium-7 also survived. These were the first elements ever formed, and remarkably, the predicted abundances from Big Bang nucleosynthesis match what we observe in the universe today. The Photon Epoch began roughly 10 seconds after the Big Bang and lasted until about 380,000 years later. During this time, the universe was filled with a hot, dense plasma of free electrons, protons, helium nuclei, and an overwhelming number of photons, particles of light. These photons were not free to travel far. Every time a photon tried to move, it scattered off a charged particle, usually an electron, in a process called Thomson scattering. This constant interaction made the universe opaque, like a thick fog that light couldn't pass through. The universe was in a highly ionized plasma state dominated by radiation. As the universe expanded and cooled, about 380,000 years after the Big Bang, temperatures dropped to around 3,000 Kelvin, cool enough for electrons to combine with nuclei and form neutral atoms, mainly hydrogen and helium. This process is known as recombination. With fewer free charge particles, photons no longer scattered frequently and could travel freely through space. This decoupling of photons produced the cosmic microwave background radiation, a faint, relic glow we can still observe today. This event marked the end of the Photon Epoch, and the universe became transparent for the first time, allowing the formation of stars and galaxies to begin. Then, the universe entered a long, mysterious period known as the Cosmic Dark Ages. During this time, the universe was filled mostly with neutral hydrogen and helium gas. The photons from the cosmic microwave background were free to travel, but stretched into the microwave range due to cosmic expansion, leaving no visible light. To human eyes, the cosmos would have appeared dark. No stars, no galaxies, only a cold and silent sea of gas. Gravity, however, was at work. Tiny fluctuations in density, seeded in the earliest moments of the Big Bang, grew slowly. Matter began to clump together, forming the first gravitational wells that would later give rise to stars and galaxies. The cosmic dark ages lasted for hundreds of millions of years until the cosmic dawn, when the first stars ignited, shining light into the darkness. Their intense ultraviolet radiation began to reionize the neutral hydrogen gas, a process known as the epoch of reionization. This reionization gradually transformed the universe from a neutral, transparent state into one that was ionized and transparent, allowing light from stars and galaxies to travel freely across vast cosmic distances. Over the next few billion years, matter organized itself into an immense cosmic web of filaments and voids. Galaxies grew through mergers and interactions, some evolving into graceful spirals, others into massive ellipticals. In their centers, supermassive black holes powered brilliant quasars that outshone entire galaxies. This was also the era when star formation across the universe reached its peak, a period astronomers call cosmic noon. By about 5 to 6 billion years ago, a mysterious force known as dark energy began to dominate, causing the expansion of the universe to accelerate. Since then, the large-scale structures of the cosmos have remained in place, while star formation has gradually declined. Today, 13.8 billion years after it all began, the universe is a vast web of galaxies and clusters stretching across unimaginable distances. Most massive galaxies have quieted, no longer forming new stars, while smaller galaxies still sparkle with bursts of activity. And the expansion of the universe continues to speed up, carrying galaxies farther and farther apart as cosmic time goes on. If you find it hard to remember the key events of the Big Bang, we've put together a timeline that you can download in the description box or pinned comment. If you enjoyed this video, don't forget to like, share, and subscribe, so together we can keep exploring the cosmos, one question at a time.